All right, the next type of application for derivatives is what I think is really cool. It's one of the reasons that I really became a math major, teacher, whatever. But implicit differentiation can take these formulas that we've already known forever, things like area is equal to pi r squared if you're working with a circle. If you take the derivative of both sides of an equation like that, you can get a brand new equation that gives you a relationship to how the area would grow as the radius grows and so on. So that's maybe a bad example because that's something you can maybe figure out without calculus. But trickier things like the area of a rectangle, the volume of a cylinder or a cone, either one of those are things that are maybe not intuitive. And so that's what section 3.11 is all about here, is not only creating new formulas, but then using them to find rates of change that would be otherwise pretty impossible to sit through and think about how they would be related. Okay, so at the beginning here, our textbook doesn't really do much of this. I wish it did. But as I said, one nice application of implicit differentiation is that we can take a known formula. These down here, you should all recognize the perimeter formula, the area formula that I mentioned a second ago. There's the volume of a cone, and then kind of the distance between 2 points. All right, so given these four formulas, we can just take the derivative of both sides. Here, we're just going to assume that everything's a variable. We're not going to be taking it with respect to L or with respect to W. We're going to kind of pretend that they're all kind of like the Y in our implicit differentiation, because more than not, um, when we take derivatives to find rates of change, we're going to be taking the derivative with respect to time because things change over time. And you can see there's no t's here. So every single one of these variables, we're just going to assume is changing with respect to time. And so that's why we have to treat it as a function, just like we did with y and y prime in our normal implicit differentiation. And so there's not really much to talk through here. We'll show the work, but here, when you take the derivative of both sides, there's no real special rule that you have to use other than, I guess, the sum rule. You're going to end up using the chain rule in part B. You'll end up using the product rule, which we're multiplying between two variables this time, along with the chain rule, and then kind of the chain rule a handful of times with this last one. So this is, once again, more or less just a practice taking derivatives and using implicit differentiation that you've had some practice with already. So for looking at our perimeter formula, if I take the derivative of both sides, then we use the sum formula to break it down into the derivative of 2L and the derivative of 2W. And from there, the constant multiple rule just says, hey, the 2 stays, but we have to take the derivative of L and W. Okay, so like some of the previous videos I've done, I'm showing a little bit more work than I shouldn't say a little, I'm showing a lot more work than I would ever expect you guys to do. I would expect you at this point to be able to mentally just say, well, I'm just taking the derivative of each term and this is what I get. But I also want to break it down this way to make sure that you're actually pausing and thinking and verifying that, hey, yeah, this is an easy one versus something that's a little bit more complicated. Right? So moving down to the next one with the area of the circle, this is the chain rule, specifically because there's, excuse me, something other than just constant multiplication or anything like that on the R. R is being squared, so R is inside the square function. Right, so here our chain rule is always, we take the derivative of the squared, so you multiply by 2, decrease the exponent by 1, and then you also have to multiply by the derivative of the inner function. So that's one thing to be really aware of here. And you've seen this with implicit differentiation, but when we find rates of changes of things that are more complicated, the rate of change of the area doesn't just depend on the rate of change in the radius, it also depends on what the size of the radius is at that moment. Okay, so you're going to see a lot of that as you go forward. Okay, in part C, we were looking at the volume of a cone. And once again, kind of working from outside in, I'm kind of breaking this down more than I need to again, but 1/3 pi is just a constant multiple, so it'll stay put. We have to just take the derivative of r squared times h. We're multiplying here, so this is the product rule. So again, our 1/3 pi just drops down. We take the derivative of the first function times the second, plus the derivative of the second function times the first. And then finally, use the chain rule on the r squared again to get 2r times r primed, along with the times h. And then over here, there's nothing to do. H prime is just H prime. Okay, so again, taking a look here, the rate of change in the volume depends on basically everything. It depends on how quickly the radius is changing, how quickly the height is changing, what the current height is, what the current radius is. So it's a much more complicated formula than what we started out with. And then finally, when you're looking at that square root distance function, we're back to using the chain rule. It's been a while since we've talked about square roots in any of the notes that I've given you. Keep in mind here that you can either rewrite this quantity using a fractional exponent, but I mentioned earlier that square roots are common enough, I would just memorize this. The derivative of the square root is always just going to end up putting the square root in the denominator along with the 2, and the numerator is just a 1. So the derivative of the square root is 1 over 2 times the square root of whatever's inside the square root. And then with the chain rule, again, you multiply times the derivative of the inside part there. And even there, just be careful. This is kind of the, quote, obvious chain rule where we can see something inside something else. When I go to take the derivative of x squared and y squared, you're not just going to get 2x and 2y. You're going to get 2x times the derivative of x. You're going to get 2y times the derivative of y because of the chain rule. It's the derivative of the square gives you the 2x. The derivative of x is what actually gives you the, quote, derivative of x. And then the next step here is somewhat optional, but anytime you can write it a little bit more nicely, you go ahead and do it. You know, some of the examples up above, there's not much to simplify, or even here, if I took the dots out and distributed the 1/3 pi, nothing really changes there. But in this one, you can see that if I factor out the 2 from this expression, the 2 here and the 2 in the denominator are just going to cancel out. So that's why all the 2's disappear. And then when you're working with a fraction especially, it's nice to write it as one single fraction. So this stuff just goes up in the numerator. Okay, so that's the formula to figure out how quickly the distance between 2 points are changing based on the current value of those, the coordinates of the points, and excuse me, the rates of change in the x and the y value. Okay, so what the textbook really concentrates on here is not so much creating those functions, but using those functions in what are called related rate applications, where here we're talking about 2 or more variables changing over time, kind of what we talked about a second ago. These formulas have 2 or more variables. Kind of the hidden variable in there is if something's changing, it has to be changing over time in this sort of perspective. Okay, so we're asked to find the rate of change in one of the variables given other types of information. Right, so this first example, I'm not going to try to break it down step by step before we do a problem. We're just going to do this by example. So here we're working with a rectangle. We're told that the length is actually decreasing at a rate of 2 centimeters per second. The width is increasing at 3 centimeters per second. And so they're kind of doing opposite things. And so this is one that would be mentally pretty tricky to try to figure out what's actually happening here. Do those completely balance out so the area stays the same? Is it growing a little bit more because the width's growing faster than the length is decreasing? What's happening here? Okay, so we've kind of seen this earlier that we have extra information because oftentimes our answer is going to depend on the rates and the actual lengths, in this case, at a specific time. So that's why we're asked what's the rate of change based on these rates, along with knowing at that moment the length is 15 centimeters and its width is 12. Okay, so the breakdown is nothing more than start by trying to figure out, hey, what is the formula that I'm relatively comfortable with from prerequisite knowledge? What formula or what equation can I use that gives me information about the length, the width, and the area of a rectangle? And of course, there's not much thinking in that one, but that's phase 1. Determine an equation that gives you the relationship between the quantities. Don't worry about a relationship between the rates. That's what we're going to create using implicit differentiation. But the quantities, as I was trying to point out here, that are referred to are length, width, and area. We know a formula for that. We don't have to do anything special to come up with an equation. It's just the area is equal to length times width. Okay, so phase 1 is come up with that sort of basic equation to start with. Phase 2 is to just use the implicit differentiation to take the derivative of both sides, again, technically with respect to time. I'm not going to write this as d over dt over and over and over to, I guess, pound it in your mind that this is with respect to time. I'm still going to use the prime kind of apostrophe notation, but be aware that when we write a prime, we really mean the derivative of a with respect to time. L prime is the derivative of L with respect to time, so on and so forth. And so when we take the derivative of both sides, that's going to give you the relationship between the rates in the problem. So based on what we did on the previous page, this should not be a surprise. We're just taking the derivative of both sides. That's a product, so use a product rule. So derivative of the first function times the second plus the derivative of the second function times the first. And now that we have this written out, I think you can probably guess what's going to happen here at the end. We're going to have to take the information that was given to us. Rates are derivatives, right? Derivatives are rates of change. So if you have a rate, those are derivatives. If you have just a given quantity, whether it's a length or something else, that is just your normal variable. So all we have to do at this point, and I guess I broke it down under here, so I'll bring it down, is we're just plugging in the information that we're given in the problem. You know, quantities that have labels that don't have the per second or any sort of time unit are kind of the non-derivative variables. They're normal, in this case, length and width, just have one length label. The rates are either labeled as rates or are going to be labeled as something as miles per hour, feet per second, in this case, centimeters per second. That per in there, along with the time unit, it tells us that you're dealing with a rate. And as we said here, rates are derivatives. One thing to be a little bit careful with here is that you do have to pay attention to the signs. You're never going to have a negative length or a negative area or anything like that, but their rates can be negative. Increasing rates, of course, are positive. Decreasing rates are negative. So that's one thing. It's a kind of a minor issue, but it's something that's easily missed. So that's why I wanted to bring that up. So from our problem, we were told the length was 15 and the width is 12. And the rates were that the length was decreasing, so the derivative is negative at 2 centimeters per second. The width was increasing at 3 centimeters per second. Okay, so as I write the rest of this out, you don't actually have to put labels in your equation. It can be kind of a hassle, especially with some of the longer equations that you sometimes run in here. I'm doing it this first time just to make sure that you see how these labels kind of tie together and cancel out into the labels that we want to have for our answer anyway. So here was our equation that we got from phase 2 up above. We're plugging in the derivative of L was -2 centimeters per second. The value of W was 12 centimeters. W prime, or the derivative of W, was positive 3 centimeters per second, which was growing. The length was 15 centimeters. And when you multiply these together, centimeters times centimeters gives you centimeters squared. This is still per second. And same thing over here. So the two labels we get are centimeters squared per second, which is good because area is measured in square centimeters. And if we're looking at the rate of change, it would be square centimeters per second. And of course, just add these together to get the final answer. So based on the information that we had here, and I guess I called this phase 4, just make sure that you're answering the question here. At the end of the day, that area of the rectangle is increasing at a rate of 21 centimeters squared per second when the length and width are at these dimensions. Okay, so just absolutely be clear here. If I went back to the original problem and changed it, so maybe the length was at 20 centimeters and the length is 12 centimeters, that answer changes. And so this rate of change in the area depends on the rays themselves, but also the actual length and width of the rectangle. Okay, so that's your basic idea. So just find an equation that gives you a relationship between the ideas in the problem. Take the derivative of both sides, being very careful to use your appropriate derivative rule, and then interpret the rates in the problem as derivatives. Anything else would just be a length or just a normal sort of information that you plug into your variable. Plug everything in. And sometimes, depending on what you have here, you might actually have to do a little bit of solving. It might not always just be calculations like this, but after you plug it in and solve for the rate that we're looking for, just make sure you label your answer. And you don't have to write a full-blown sentence for me, but at least tell me that it's either increasing or decreasing along with the correct label. Okay, so we'll do a couple more examples just to give you an idea of what else you might run into, but after that, there's not going to be anything new. It's just all dependent on being able to write out the information, or sorry, the different information with each problem in a meaningful way. So here we're working at a softball game. There's runners on first and second base. When the ball is hit, the runner on first base begins running at 15 feet per second. The runner on second base begins running at a speed of 20 feet per second. Okay, so I guess a little bit of extra information here. In softball, the bases are 60 feet apart. They do form right angles, so we're kind of looking at a square along the way here. And then the two question we're asked is part A is to go ahead and find the equation that gives a relationship between the distance each player's run to the distance between the players. And here I almost didn't type this up, but I wanted to make sure that we're clear that this is we're just looking at the first moments after the ball was hit. After 3 seconds, this runner on second base would reach third base and would change direction. So we're not worried about that. We're not trying to figure out some sort of crazy relationship where things change directions after a while. That would go back to being a piecewise function. So we're just going to assume that t is between 0 and 3, so that neither one of the runners reach the next base. And then once we have that equation, we're going to do what we just did and find the rate of change of the distance between the two runners as they're going on their two different paths. Right, so this one you can kind of take a look at and see there's no formula that's at least well-known formula that you can use to work with this. And so we're going to have to create this equation ourselves. That's why I split this into its own problem here. But anytime you're making your own equation, you have something physical to think about, just go ahead and sketch a picture. Okay, so we're going to draw the baseball diamond, and then we'll let D1 represent the distance the player in first base has run, D2 be the distance the player in second base has run, and this regular D is the distance between them. Okay, so just to show you that picture real quick. But here's your baseball diamond. I didn't bother to try to put it in home plate with this weird shape, but there's the distance the player 1 has run after a certain number of seconds. And keep in mind, this is not at any specific time. This is just after a generic t seconds. This runner is a little ways. The runner from second base would have run this distance. So here's distance 1, here's distance 2. And of course, the distance between them is going to be this diagonal line. Okay, so there's still some blanks to maybe to fill in here, but hopefully once you get this drawn, you take a look at this and say, well, wait a second, I've got a right triangle here. There's two main ideas that we can work with right triangles. One is the Pythagorean's theorem, a squared plus b squared equals c squared. So if we can figure out what this distance is, not an exact distance, but a distance that depends on these variables, we can use Pythagorean's theorem. The other thing that you can do with right triangles is maybe use trig functions. Here, that doesn't really make sense because we don't have any information about the angles here. And so we're not going to be able to take sine, cosine, tangent of anything here. So this one is going to be a problem where we're going to be using the Pythagorean's theorem. We have a right triangle. We have an expression for one length, an expression for the hypotenuse. And knowing that the bases are 60 feet apart, even though this distance is not the side length that we want in our triangle, we can find that very quickly just by subtracting. Right? If the whole distance is 60 feet, she's run or he's run, whoever it is, has run d1 feet, then the remaining distance is 60 minus this d1. Okay, so setting up Pythagorean's theorem then, we have the hypotenuse squared is equal to one of the side lengths squared, so the 60 minus d1 squared, plus the other side length squared. Okay, and that first part, that's the only thing that makes any of these problems different. As soon as you figure out what the equation is that relates, excuse me, as soon as you figure out that equation, everything else is just literally take the derivative of both sides, figure out how to interpret the information from the problem as rates or extra information to plug into the problem, and then answer the question. Okay, so moving on to part B, the first part of part B, where we're asked to find the rate of change between the runners, is the same thing that we did before. We're just going to take the derivative of both sides. I should take a step back here. I left it in this format because there's no need to get anything solved when you're using implicit differentiation. If you really, really wanted to, you could take the square root of both sides here and get d is equal to square root of all of that, and then take the derivative of both sides and get an expression for d prime immediately without anything else. But then you have to take the derivative of that square root function, and that's not always the easiest to work with. So I would tend to leave it in this format and just realize that implicit differentiation is nice because you don't have to have things solved. You take the derivative d squared, where you derivative of the outer function will give you 2d, but then you have to multiply by the derivative of the distance, and then take the derivative of the squared, so 2 times all that, times the derivative of the inner function. So be careful here. You take the derivative of the inner function, the 60 disappears, but the negative sign is still in front of the d1 as you take its derivative. And then again, derivative of the square function gives you the 2d2, multiply times the derivative of that second distance. And so again, just be very careful with your chain rule. Anytime you have exponents on any of the derivatives that you're taking, sorry, any of the expressions you're taking the derivatives with respect to, you're going to get both the original variable along with the derivative of that variable. Okay, so now it's just a matter of figuring out what values to plug in here. Okay, so that was a typo. I changed my mind earlier. So going back to the problem, it asks us to find the rate of change of the distance between the runners 2 seconds after the ball was hit. Okay, so we're trying to determine the values of the rates and the distances when time is equal to 2. Okay, and so for the distance that the ball players have run, it's just a matter of using the distance formula from algebra. Right? We were told that the player on first base runs 15 feet per second. He's doing that for 2 seconds, so distance is speed times time. He's traveled a total, sorry, that's walking. I didn't realize that little circle was going to be in our way here. But 15 feet per second times 2 seconds means the first runner's ran 30 feet. Same idea here, but the second runner is running 20 feet per second. So after 2 seconds, he's run 40 feet. So that gives us the values for D1 and D2 that we're going to plug in here. Keep in mind that the derivatives of D1 and D2, derivatives are rates of change. Rates of change in this perspective are speeds. So these are the two rates from the original problem. Just give us the derivatives of those two variables. And then I guess maybe the hardest part, not that it's always really hard, is that we have to go back to that first formula. Okay, we're not using this because there's too much information here, but go back to the first formula that we got from Pythagorean's theorem so that we can figure out what is the distance and t equals 2. Right? We know the base runner's distance at t equals 2. We know the other base runner's distance at t equals 2. That means we can find the total distance at t equals 2 as well. So we take that formula, we put in, and d1 is 30, d2 is 40. And so this just run through the Pythagorean's theorem, you end up with 30 squared plus 40 squared. If you know your Pythagorean triples, I guess you can get 50 without showing all this work, but you do end up with the value of d being 50 feet, which I should have labeled here. So I'll go ahead and put that in. Okay, and now that you know everything that you need to plug in, phase 3 is just plug it in and solve whatever you need to solve. So again, we're looking at the formula up above. It's 2 times the distance we just found to be 50 times the rate of change of the distance is what we don't know that we're solving for, is equal to 2 times 60 minus d1 times the negative derivative of d1. So the derivative there was 15, but we need the opposite, so it's negative 15. And then 2 times the distance of player 2 times the speed of player 2. And all of this over here is just arithmetic. It gives you 700. Divide both sides by 100, you get that d prime is equal to 7. Okay, so as I said in that first example, if you want to put in 60 feet minus 30 feet times negative 15 feet per second and put all those labels in and keep track of all those labels, it will give you the label as you work through the problem. But here we know that the derivative is change of, excuse me, distance with respect to time. So our label here needs to be distance divided by time. And of course, everything else was given to us in feet per second. So our speed or our rate here was also in feet per second. This is a positive rate. That means that the distance is increasing at a rate of 7 feet per second after 2 seconds. Okay, so I guess I will say in all the different practice problems from the textbook or the assignments, this is kind of closest to the most typical sort of problem where it's not necessarily just, hey, here's a formula that you know, take the derivative, plug numbers in. There's oftentimes just a little bit of thinking and setup to get through a problem. Okay, so let's just do one more. And after that, I'll leave you guys to practice through assignments and absolutely shoot me an email if you have any problems at all. I know word problems are always tricky. But in our last example, here, you know what, I'm just going to show you the pictures. You read through this or I talk through it. So as before, our first objective here, since we're not going to be given an equation to work with immediately, is to draw a picture so we can make our own equation. So we know a police officer pulled into an alley, stopped, put his little rotating light on top of his car. I don't know if cops still do that, but that's how I'm making this problem. And the light here is spinning around at a speed of half rotation every second. And we're told that the cop car is exactly 15 feet, or that light at least is exactly 15 feet from the wall lining the alley. And so the angle theta represents the amount the beam has rotated after a certain amount of time. So here it's maybe rotating clockwise. So here's theta. rotating with respect to when the beam is exactly perpendicular to the wall. Okay, so this is all the information that we were told in the problem in diagram form. And this one doesn't break it down. It just flat out asks us, how fast in feet per second is that beam? So we're talking about the point right here. How fast is that point moving along the wall as, at the moment when this angle theta is 80 degrees? So this one didn't break it down for us, but we still have to follow the same basic idea. We need to come up with an equation that gives us a relationship between the angle theta, and because we're looking at for the speed along this wall, to find the speed, we're going to need to know the distance that it's traveled along the wall. So even though we don't know that, we need to put a variable here. Okay, so we're looking for an equation that gives us a relationship between this angle theta, the 15 feet that we know, and the distance here that we don't know. And we don't need to know any other distances. We don't need to know any other areas of the wall. We don't need to know the length of the hypotenuse, because we're not asking about how the hypotenuse is changing. We're asking about how this distance is changing. And so taking a look at this, this is again a right triangle, but be careful here. We can't use Pythagorean's theorem because we only have two side lengths. And I just got done saying we don't really want to put a variable over here and use Pythagorean's theorem, because that's not going to give us any sort of meaningful relationship that helps. And so instead of knowing this third length, we know the angle. And as I mentioned in the other problem, as soon as you have a right triangle where you're working with angles, that just becomes a trig problem. So we have the angle measured here, the side opposite that angle, the side adjacent that angle, opposite and adjacent sides. That is giving you information about tangent. Okay, so if I take tangent of theta by definition, in right triangles at least, by definition is the opposite side divided by the adjacent side. Okay, so there's a little bit of talking through that, but we get a relatively straightforward equation here. The tangent of theta has to be equal to x over 15. The next phase, as we've seen earlier, is just to take the derivative of both sides with respect to time. And again, just make sure that you're using any rule that you need to along the way. So tangent of theta is definitely going to need the chain rule, because we have to take the derivative of the tangent function and the derivative of the theta as a function itself. So the derivative of tangent is secant squared. Keep the inner function, but then we also have to multiply by the derivative of that inner function. On the other side, you might be tempted to use the quotient rule here, but be careful, there's no variable in the denominator. So we've seen this in previous talks. If you have just a coefficient down there, this is nothing more than the constant multiple 1/15. And so we just keep that 1/15 and take the derivative of our variable. So we get x primed over 15. Okay. And now that we have that relationship, now it's just a matter of, plugging in our value of theta, which was told to us. We know that theta from the problem was 80 degrees. We need to plug in theta prime, the rate of change of that angle. Well, be aware up here, the rate of change of that angle is going to be 0.5 rotations per second. We just have to do a little bit of unit conversion. And then finally, x prime is the rate of change of this distance x, which is the speed that we're looking for. Okay, so one complication here is said this, I guess it was a previous set of notes. Even though this is given to us in degrees, if you're working with a physical relationship, whether it's in calculus or physics or elsewhere, you really need to be working in radians. All of the nice formulas that give us relationships between distance and an angle measure, like arc lengths, things like that, you have to be working with radians. So the first thing that we're going to do here is actually convert, we're going to convert the information we're given from working with degrees or rotations into radians. So we said that the value of theta is equal to 80 degrees. We need to convert that to radians. Our conversion factor is pi over 180, so that the degree symbol cancels out here, and you simplify your fraction, it will be left with 4 pi over 9 radians. And then the second part of this is that the rate of change of that angle is its rotation. Okay. And so we don't want to be in rotations per second. We need to be in radians per second. Well, one rotation, right? One rotation is 2 pi radians. So just replace the word rotation with 2 pi radians. Do your multiplication, and you're going to be left with pi radians per second. Okay. So that was a little bit tricky, but that's the last remaining hard part. Everything else now is just plug the values into that equation and see what we get. So we're taking secant squared of 4 pi over 9. The rate of change of theta, we just calculated to be pi. We don't know the rate of change of x. That's the speed that we're looking for, and the 15 just stays. And from there, it's just a matter of making sure that you're typing it in your calculator correctly. Maybe I should write this to be a little bit safe here. So when you're looking at the secant function, there's certainly no secant button in your calculator, but remember that the secant function is reciprocal of cosine. So if you're putting this in your calculator, so that arrow does not say that we're solving here, but if you're looking at that, let's get rid of that in case. If you're looking at that secant squared function, first of all, we've actually talked about this with the chain rule. That is absolutely the same thing as secant of the angle first, then squared. So if you're typing that in the calculator, that's one thing you have to be aware of. And then from there, I'm probably going to end up going down a page by accident. But from there, if you're working with secant, secant is reciprocal of cosine. Reciprocals algebraically, when you type it in the calculator, always 1 over whatever you started with here. So I should have been a little bit more careful when I said that. So if I'm talking about the reciprocal means 1 over something, and the reciprocal of secant is cosine. So if I take 1 over cosine, I get secant. So this is the expression that you would need to type into your calculator in order to go through and calculate this. So just quickly, all we did here is multiply both sides by 15 to get the x prime by itself. Then you're typing all of this into your calculator at once. It spits back this number. And of course, remembering that the derivative we're working with is a rate of change of the distance. So this is the speed that we're looking for. So the beam travels along the wall at a speed of 1,563 feet per second when theta is equal to 80. Okay, so just a quick side note here. If you convert this to miles per hour, you can just Google it or do your own conversion. That ends up being about 1,000 miles per hour. And maybe it was a little bit more than that, but it was at least 1,000 miles per hour. I always have fun with this. Maybe you guys won't care about this at all, but working with the rotation like this is as close to people being able to visualize infinity in real life as you possibly can. Right? You can imagine, the spinning light. That you can see that in real life. Now you would have to have infinite vision like Superman or something like that. But if you followed that path of light, let me go back up here, you're able to watch that light go down the wall, and that wall was infinitely long. You'd be able to see the speed of this beam go to infinity. Okay, so I think that's pretty cool. Maybe it's just a side note that you guys don't care about at all. But I guess back on topic, not that there's much more to be said here, just another recap. The main idea is to figure out how to come up with an equation that gives you a relationship between the quantities. Don't worry about the rates. Sometimes you have a formula, sometimes you have to draw a picture. After that, take the derivative of both sides using implicit differentiation in the chain rule. And then it's just all about interpretation. Every once in a while, you'll have some unit conversions like this, but just go back to the problem, figure out what the angle is. In this case, figure out the rate of change of the angle, plug those numbers in, solve for the missing information, and you're done. Right, so I guess that's where we'll stop for the day. And again, if you have any questions or concerns, absolutely email me. See you soon.